Good morning, everyone. My name is Wassim, and I'm presenting today our work titled Deflection Behavior of Beams Prestressed with Bonded FRP Tendons, co-authored with Professor Peter Bischoff and Professor Hani Nassif. As a background on our work, we know that our knowledge of post-cracking deflection is still limited for pre-stressed concrete, and specifically for pre-stressed concrete with FRP tendons or fiber-reinforced polymer tendons. The current calculation methods are problematic because they still use modified versions of Branson's approach, which was originally developed for reinforced concrete members. Now we're using it for pre-stressed concrete members, and we know that the behavior is different. For members pre-stressed with FRP, not pre-stressed, reinforced concrete, we use a softening factor. And so for a pre-stressed concrete, but we got to check if the softening factor is gives good results or not. And for that assessment, we need to use an experimental database. We have an extensive database from which we selected some 38 beams that meet the criteria that we set up. So this is a chart that shows a moment versus curvature for either type of structural member, non-prestressed or prestressed. So for the non-prestressed, we have the stiffness up to the cracking moment is related to the whole section, the gross section, and after cracking, it is related to the cracked section. For the prestressed, it's almost the same, except for having negative curvature or deflection due to the pre-stressing, and we have a higher cracking moment also because of the pre-stressing. So our current study assesses many different approaches for computing immediate deflections as opposed to long-term deflections for FRP pre-stressed concrete flexural members that are cracked under service load. So it's specific to this type of members. Okay, so the first set of methods that we used for validation and assessment is the most common one, Branson's modified approach. And what you see here is a softening factor that is specifically used for beams with FRP tendons. Now, this softening factor is a factor that's less than 1. What it does is it accounts for the reduced modulus of elasticity of the FRP compared to steel. And of course, we know that when we're computing deflections, the main parameter or the main expression that we use is for IE, which is the effective moment of inertia that's a weighted average between the gross, the full section, and the cracked section. Now, this is Branson's modified approach, so we will be assessing it, of course, different values of beta, different expressions. This is the first one. The second one is the effective eccentricity approach, and this approach would account for the varying eccentricity of the tendon beyond cracking, because we have a smaller section now. We have a shifting in the centroid of the section, and this explains these two approaches. So what you see is moment versus deflection, and of course we have mainly two branches of a moment deflection curve. One is the pre-cracking branch, which is stiffer, it has a higher slope, and we have a less stiff, lower slope beyond cracking. What IE does is that it blends these two together. So, because the deflection is a summation of an uncracked response and a cracked response. So we have deflection until cracking, and then we have deflection beyond cracking. IE would blend these two together. Now, what you see here in the first one on the left, Branson's modified approach, we have, so IE is presented here as if it is the slope. It's not really the slope, but it's a part of the expression of the slope, in addition to E and others. So we have two, the blue and the red. One of them is shifted, so the response is shifted. Now we will be assessing different shifting responses. One starting from 0, which is the red one, and the other, in our case, we did decompression moment. Some others use M-balanced or M1. I'll be talking about these later. The second approach, the effective eccentricity approach that you see on the right, uses the moment that's the moment that's product of the effective force and the eccentricity, effective eccentricity. So what you see here, dP minus y bar E, is the effective eccentricity of the tendon. The other approaches that we have, one is the PCI-based bilinear approach. Most of you are familiar with the PCI approach, and I'm going to go to the next slide just to show how it goes. So PCI approach divides the response of the member into two, one pre-cracking and one post-cracking. So the deflection will be a summation of each. It does not really use an expression for IE, but the expression that we have was one that we developed that matches exactly the behavior. And the other two approaches are by Professor Bischoff that form a basis for our proposal for 318 to adopt a new set of equations. And they have a shifted response as well. That's M1. Now here's the thing, for the expressions of IE are completely different from those previously presented by Branson and the modified versions of Branson. So you can see IE, it's still in terms of I crack and ITR, and of course the cracking moment and the applied moment, but it's not a weighted average anymore. For the validation, we selected 38 beams out of a much larger database, but we did exclude many studies that are not necessarily relevant for our case. For example, those with different types of concrete, say fiber reinforced concrete, those with reinforcement, steel reinforcement. We had to exclude these because we are solely focused on the behavior of FRP. So these are the ranges of the beams that are selected from the literature. You have the range for the strength, the modulus of elasticity, the pre-stress, the ratio, and the reinforcement ratio. Now, for validation, we did select from the load deflection curve of each and every member. We did select random points beyond cracking. So we have the load and the deflection, and we will be using our methods that we have to find the deflection and compare it with the experimental deflection. And here is what we got. Okay, so for the first approach, the Branson's modified approach, of course we did it with different shifted responses, with different expressions of the softening factor beta. We have many expressions, but we did select 3. These are mentioned in the 440 and in another research by Dr. Bischoff. And you can see that in these charts or plots the calculated versus the experimental deflection, which means that whatever value we got is in the y-axis, and whatever value from the experimental from the experiment itself is on the x-axis. And whenever you see the point above the reference line, which is the 45-degree line, then we have an overestimation of deflection, and when we have it lower, then we have an underestimation of deflection. Now, for the first plot, you can tell that we either have it overestimated or underestimated. So the blue and the red are extremely underestimating the deflection up to a ratio of 2.2. And a ratio of 2.2 means the calculated divided by the experimental, which means that we have up to 120% overestimation of deflection. The other one does underestimate with a mean ratio of 0.65, which means that it's 35% lower on average. The other one, on the other side, you have it with a shifted moment, which is the decompression moment, and the mean ratios are 0.4 and 1.2, depending on whether we use softening factor beta or not. So you can see beta equals 1 means no softening factor, just in the case of steel. We have it extremely underestimating, but the other one is slightly overestimating, 20% on average. Now, this is the effective eccentricity approach with and without the softening factor. Without the softening factor, it's very much underestimating, 0.32. The other one has a very good mean ratio, 1. It's perfect, of course, but that's a mean. That doesn't mean that each and every value is well estimated. Now, the other two approaches, the bilinear approach and the Bischoff approach, also slightly overestimated by 12, 23, and 30% respectively. And we did use an integration factor, and that integration factor would account for the different states of the section all over the member, because, as you know, when we say that the section is cracked, it doesn't mean that each and every section has cracked. We still have uncracked sections that will contribute to the overall stiffness of the member. And with integration, of course, we expect the member to show a higher stiffness and thus lower deflection. So the observations were that Bischoff modified approaches and as well as the bilinear do slightly overestimate, which is in fact a good thing. I mean, think about it. Slightly overestimating deflection is we are on the conservative side. If we assume the deflection is 1.2 and it is in fact 1, that's not necessarily a bad thing. The opposite is not true, however. We don't want to underestimate deflection. So we observe that we do need the softening factor, specifically for the effective eccentricity approach, and for Branson's modified approach with the shifting moment. So this is a summary of the results. We did look at one other thing, which is using the gross moment of inertia instead of the transformed moment of inertia, and that's for the uncracked part of the section, because it's easier to just use the concrete section. And we found that we have slightly, so the estimation has slightly increased in either method by like 5 to 10%. So we have some upcoming publications that's based on this work and other work that we have done, one of which is proposed ACI 318 equations for immediate deflection of prestressed concrete members. So we have an approach that we did work on over the past years. We have it proposed to ACI 318C, and we are hoping that it will be adopted by the ACI 318 code. And we have another relevant publication in the Concrete International. And last, I would like to acknowledge the C2 Smart Research Center and New Jersey Department of Transportation for their support. And I would like to thank you for your attention, and any questions I'm ready to take. Thank you.